So welcome back, everyone. I will just start with a few words about the Dragonstone, a little bit of what was planned for you to understand why we do things the way we do at the moment. And so this is an extract of the project. You see also the mouse moving somewhere? Okay.
Yes, we see your mouse. Yeah.
So here what we are doing exactly is the S2S fundamentals, but you know, in this, what was initially planned in this first part, day 1 to 5 of the Dragonstone Summer Institute, we had you know, concepts, big picture overview, etc. With short visits to local field examples. Okay, so we are doing everything here except the local field examples, and that's what we will do. And I will show you that's what we will do in the second part when we meet in May. But also in May there will be a big excursion, okay, which is day 6 to 12, where all the PIs will come, hopefully. And in which we will go from Tremp, close to the source in the Pyrenean routing system, all the way down to Zumaya. And I will give you the dates, but this is normally mandatory. And in the last part, you will have a break. And in the last part of the Dragonstone Summer Institute, you will be in Total, in Pau. And there you will do a mix of technical and soft skills. There's a lot of chatting in the next room. Do you hear that? Do you hear people chatting, or it's okay? I only see Alex. So
yes, I can hear them.
You can hear them? Wait a second. Sorry. Okay, so here I want to show you the planning of an extract of the planning. So here I've put, this is May, 26th of May, so you can put dates in your planning. In fact, instead of doing a week where we would have half a day on the field, half a day with computers and courses, here, and this was planned to be during 5 days, so effectively two and a half days of field work. Here we will meet during 3 days, 26 to 28, and this will be field, and I wrote evening-long discussions with computers. So this is end of May, and then in the evening of the 28th, normally I think the PI, your supervisors, will join us. So this is myself, Jean-Brown, François, Cécile, Alex. I mean, hopefully, maybe also Thierry Haddad, maybe Julian Clark. But this is 3 days of field work essentially, where you will apply the concepts and skills that we've learned this week. Then we have what I call the big excursion. All ESRs, all of you, and all PIs, and it's also open to the broad community, but we don't know how much people we can really take. Here you have a weekend. I wrote a holiday, but it's just a weekend. So for you to relax in between the big excursion and the time you will spend in Pau, 4 days in Pau. So here during the excursion, we hope to you know, do a lot of science discussions, networking, you to know everybody. We will devise a good program also for the evenings, and potentially to already start solving scientific problems, you know, by discussing with all of you and all together. That's the ESR weekend, and then technical and soft skills training in Pau. I just think it's important really to have those dates. Of course, you may say I'm a dreamer, but it will be good to for you to set those dates in your calendar, not to book anything else, like a wedding in that period, for instance. Okay. So Dragonstone, and I have just two more slides on the Dragonstone. As you know, Dragonstone is one of the episodes of the Game of Thrones, and somewhere here down there in the episode, you find the characters, the characters of the series digging for some kind of strange stone, Dragonstone, that can be used to kill zombies. Bref, this is a very nice artist view, but as you can see, there is real photogrammetric data behind, and there is really those things exist. And this is in fact Zumaya, so that's where we will end up by the end of the big excursion on the 4th of June. And if you want, that's where you can also spend the weekend. So some of this, the large stairs don't exist, huh? But this is the real, it's actually nicer than in the Dragonstone episode, I find. This is the real plage, the playa or the baya in Zumaya. So as you can see, there is very nice outcrops, and there are several golden points of the stratigraphic history, and there is also the PETM boundary in this area. So that's the kind of the end point, the turbiditic end point of a source-to-sink system that we will follow all along on the southern margin of the Pyrenees. Like François was showing this morning, modern day examples. This is the ending point of a fossil example of a sediment routing system. Okay, so after this small introduction, and don't hesitate if you have questions later about this, my role today in the next 2 hours is to do the two first points of this outline, and I will give you the PowerPoint or the PDF of this presentation. But you can always do a print screen. It's one of the most helpful buttons if you want to take notes. So I will just today do the definition of source-to-sink very briefly, and then a small historical perspective of the source-to-sink approach. The historical perspective is more of a vector if you want to speak about different aspects of the source-to-sink approach and why we are now into doing source-to-sink. Okay. In the next part of the course, we will do gains and limitations of the source-to-sink approach. And I have this chapter 4, terminology and key numbers, which I may actually do before gains and limitations, where we will speak about the major processes and major order of magnitudes of those processes. So I will often speak about the same things as Jean and François. We will probably repeat things, but with perhaps a different perspective. So for you, it should be a good thing. Okay, so for the definition of source-to-sink, it's one of the very simple diagram, and I wrote this definition, which can be improved or modified, but I think it's good to start with some definitions. And here we really speak about the S2S, source-to-sink approach. Okay, so it's an approach which consists in studying sedimentary systems as a whole. I think it's important, from sources to basins. It's obvious from the title, but it's really important to have it in mind. So if you really do source-to-sink, then when you study sedimentary succession, you should actually force yourself to think about the source and the transfer area. And it's not so obvious as it sounds. And I just added that it involves the quantitative characterization of the processes that are involved in the production, transfer, and deposition of sediments. That's also obvious, but it also, if you stick to the definition when you do source to sink, it also forces you to try to put numbers on what you think about. So often in the past, of course, people were thinking, oh, this must be, I'm seeing a conglomerate in my succession. Oh, this must be a tectonic event. Possibly, but with what number, when, what rate of tectonic processes could produce the flux needed to do this conglomerate, for instance. So if you try to stick to some sort of definition like that, it will force you to try to characterize numerically, quantitatively the processes. And so in theory, the approach, you know, is applicable to quite a variety of settings, whether they are geodynamical or climatic. Like François was showing this morning, you have source to sink systems virtually everywhere, and also at many different scales, very large scales to very small scales. So this is the very simple definition. Now I'd like to start the history of the approach, and I start with the same diagram or close diagram to what François showed this morning. It's the fluvial system of Stanley Schum, and that's a 1977 book. And this is probably figure 1 of the book. So you have a drainage basin, a zone of sediment production. You have a zone of sediment transfer and a zone of deposition. And so, I mean, this was already there. It's of course in the mind of everyone. Stanley Schum was more of a geomorphologist, but he really did work in sedimentology as well. And this is, again, this is also obvious, but until you start to draw it and think about it, it's not necessary in the mind of everyone. And when you do research, often you focus on one aspect and you forget about the others, especially in the ancient, when only what is here is remaining. So I will go through different stages that I think are major for the development of the source to sink approach. There is one aspect that I do not cover here and that you should be interested in, and probably François can cover that more than me and at another moment, is the aspect of provenance, which has always been as well some sort of source to sink approach. So different stages, and I have collapsed them into different periods of time which may overlap. And one of the first important period of time is the 80s, 90s, even if it starts a little before and finishes a bit after. But the 80s, 90s, I see as really marked by sequence stratigraphy. And I put the time or the era, the period of the all eustatic. It's an English translation of what we say en français, le tout eustatique, is when really people were focused on eustatic variations as a main driver of sedimentation. Here, I just put one of the emblematic diagram, but you can find many different ones. Diagram that look like that. It's diagram derived from Peter Vail, the Exxon School of Sequence Stratigraphy. In the upper part, most of you know that, but perhaps not all of you, depending on where you come from. In the upper part, you see a cross-section through a passive margin. And you kind of have a plateau here, a shelf edge, and then a basin. So very schematic, very conceptualized vision of a passive margin, but which derived from a lot of data from the oil industry at the time. In particular, those of northwestern Africa that François was speaking about. And so that's a cross-section. And here you have what is called a Wheeler diagram. Perhaps you also know that. Here, the horizontal distance is the same as here. So it's distance along the margin. But the vertical axis is time. So you go from the beginning of the succession, and here is the end. And so this represents where does sedimentation take place with time. So in the first moment of sedimentation, you have sedimentation here. And then at some point you see you have erosion, and then you shift the locus of sedimentation towards the basin. That's this accumulation here, the basin floor fan. Then there's the low stand wedge, etc., etc., transgressive systems tract, high stand systems tract, and shelf margin systems tract. So these two diagrams are really emblematic of sequence stratigraphy of those years, because they really contain a lot of information. So nowadays we often take sequence stratigraphy as something trivial or something very perfectible, something that has a lot of defaults and weaknesses. It does, but in the 80s and 90s, this was a major advance, and we should be aware that maybe the way we do source truthing now in 20 years will be seen as very primitive as well. So in those years, I think the major advance of sequence stratigraphy was that it was explaining where sedimentation takes place at any moment of the succession, and what kind of sedimentation is taking place. So the famous systems tract, the ST, are a set of sedimentary depositional environments. So for the oil industry, to know that during the low stand systems tract, you have very different sedimentary environments than during the transgressive systems tract, is a very useful information, because depending on the depositional environment, you have different type of rocks and different type of spatial organization of rocks. During the transgressive systems tract, for instance, you may have inside valleys, longitude, very long morphological bodies that are filled with sand and encased into clays. During the low stand fan, you may have much more fan-like deposits, also encased in clays. But all of those geometrical information and lithological information are fundamental for the exploration of basins. And also, so there is clearly an applied aspect, but also this is the time of the all eustatic. So there's also a very important aspect, is that thanks to sequence stratigraphy, we could use the stratigraphic successions to derive a major variable of Earth history with time, eustasy in this case. It's not Burbank and Anderson, but it's, for me, one of the most important papers, and a lot of people have read this paper, of course. But it's one of the papers that really started, I think, the need for more quantitative geomorphology. And I wrote also dates and rates to better estimate sediment fluxes. You will see that I like the expression dates and rates. You will see that in a lot of what we do, knowing the age of what we look at is major, because only if you know the age can you distinguish between cause and effect. Okay, so if we really know the age of the impact, at the KT boundary, and if we can prove that the impact was before the end of the dinosaurs, then we can say it's a probable cause. If the impact was after the end of the dinosaurs, then it's not a probable cause. Okay, so the age of what we look at is really major, and it can also give us rates. You get a duration and the magnitude, then you get a rate. And so a lot of that is in this discussion. And this is a paper, again, I didn't put the full reference, but it's a paper by Peter Molnar, Philip England. And this paper you can find in Nature. And I can only advise you to get it. For me, it's like books or papers. You will have to read it probably 20 times, and when you in 20 years when you read it again, you will have a different view on it. But this paper was famous. Is very famous because it puts together climate and tectonics. So I will let you read it, but basically everything is in the abstract here of the paper. In this paper, what is said is that usually, a lot of the high, we know that the alpine mountain ranges have high altitudes, and this has been often ascribed to late Cenozoic uplift. Okay, because of different observations. But what Molnar explains in this paper is that actually this may be just an effect of a late Cenozoic change in climate. Okay, so this is really the chicken and egg problem, and so this was a clever title, but the whole paper is clever. But in fact, in this title, the whole paper is summarized. So that's really the art of the perfect title, because basically Molnar says what we think is due to tectonics could actually be due to climate, and we don't really have the timing, and we don't really have the ways to distinguish one of those. Basically, he poses the problem, and so you can find this paper in a plethora, in many introductions of tectonic geomorphology and quantitative geomorphology and sedimentology and tectonic papers. Okay, it's a justification. We try to understand whether climate actually changed, how it changed, and if it was a possible cause for increase in exhumation, increase in erosion, and the elevation of mountain ranges. And we also try to be more accurate in understanding the timing of uplift. Okay, so this is a major, really a major paper. I can not emphasize it enough. Also, you will see how precursor it is in the use of, for instance, the curve of delta O18, which was not as good as it is now. So this is 1991 paper, very early, 30 years ago. Okay, I continue on quantitative geomorphology and dates and rates. I think a very important aspect of those years was really the development of many new tools that could be used. Geodetic tools, for instance, with satellites. This was really the beginning of satellite imagery. François spoke about a DEM this morning, digital elevation model, and this was a major development. But here I take this image because that's also the cover of the Burbank and Anderson book, and that's that's a paper by, again, I need to give you the reference, but that's a paper by a group of French and American authors, and they used radar interferometry, which you can get from satellite imagery, to provide an image of the deformation during the Landers earthquake in California. So it's a, if I'm not wrong, it's a little offset of the San Andreas fault system. And this below is a model where you have a crack here in an elastic domain, and you put this elastic domain to rupture along this crack, and you see the deformation, the velocity of the deformation during the earthquake. And this is what happened during the Landers earthquake. So of course there is a comparison between these two images. So, I mean, the image above, maybe we are attracted by the major part of it, but still the image above really looks like the image below and suggests that the media here, the crust here, behaved in the way predicted by theory. So thanks to satellite observations, which have been developed for totally different thing initially, we get an extremely interesting measurement of ground deformation, and so that's I think a major advance. Here I just wanted to show one digital elevation model that, I think everybody now knows how to interpret, but this is one that I took from the Shuttle Radar Topography Mission, SRTM, which were freely available at a 30-meter resolution. Maybe now there is much better, but this gives already a very good view. You see Geneva Lake, which is a glacial lake, a little bit like what Francois was showing this morning for the Great Lakes of North America. You see Geneva, where I am now, the Rhône Valley. Benjamin is from here in the Rhône Valley in Vallis. The Rhône then goes down all the way to the Mediterranean. And here I just used this DEM to look at these rivers and show how asymmetric the valleys are, for instance. So thanks to such data, we can accurately measure the relief, and it's of course been used a lot for the source, but we also have images of the seafloor that are also impressive. If you look at the recent images of the Gulf of Mexico seafloor, sea bottom, it's also amazing the images we have. And so this has been made possible also like the one before, not only thanks to satellite, but I forgot to say about computers, of course. So we have better and better facilities to do these things. But honestly, when I did my PhD in 2000, looking at those DEMs were absolutely fascinating, and we were spending hours just looking at them because this was almost not existing before. Before there was only pictures, those Landsat photo that people were also scrutinizing very, very enthusiastically. Still on something very important, some very important development, I think, for all of you, is the knowledge that we have access with GPS of modern fields of deformation. So this gives us access to velocities of deformation, velocities of uplift, and so that's super important. Here, for instance, that's a paper by Pietro Sternai, who is also in the network. He's in Milano, and here in this paper, Pietro made a synthesis of the vertical displacement rate, the modern vertical displacement rates around the Alps and in this part of Central Europe, and where you see that the Alps are still going up in some places. And then, of course, with those data, these are great data to try to discuss why is this linked to tectonics? Is it linked with the melting of ice caps in other places? We can look at volcanoes, magmatism. We can look at the effect of sea level rise, etc., etc. So I think that's also a major development. Now, in tectonic geomorphology, this was also absolutely major, and probably several of you will be using that. Broadly, we can probably call it thermochronology. I'm really not a specialist of that, but it's basically how to date when certain minerals crossed a certain depth in the crust on their way up to the surface. Okay, so if you date, here you see this little T cooling. If you date that the mineral you have in your hand, you can say this mineral was 20 million years ago at a certain depth, which corresponds to a closure temperature, may say, I don't know, 2 kilometers. Then you know that this mineral has traveled from 2 kilometers down there to the surface in the last 2 million years. Of course, there are complications there. Now, how much time did this mineral spend at the surface? But if you just go and measure, you know, the zircons or the apatites in a basement rock in the Mont Blanc, you measure it here where my mouse is, not in the basin. And there you can really say this mineral has been covering the 2 kilometer of distance in 20 million years. So this gives you a rate of exhumation, okay? Some purists will say a rate of cooling because we don't really know the depth at which this cooling took place. So we don't really have we don't always have a correspondence between temperature and depth, but that will be my next slide. But this is major because this gives us access, and there is a whole range of thermochronometers. This gives us access to exhumation erosion rates that are, of course, fundamentally important. This is one major information when you study the source area, for instance. And this has led to, this was really a revolution in geology to be able to discuss that. Of course, this existed before in the form of metamorphic petrology, when you date, you know, the exhumation of blue schists, and you date their formation, and you date the different minerals in certain type of metamorphic rocks like eclogites, etc. You also do basically thermochronology, but at different time scales. This gave us a lot more precision because we realized that actually even very close to the surface, and now some people like Fred Herrmann in Lausanne have been developing very shallow thermochronometers that allow you to tell something about the last kilometer of exhumation. So you have a range of timescales and rates that you can derive to improve your understanding of the history of exhumation. And you'll see, I mean, we do, in the paper by Brian Romans, we do a little review of that, but there's a very good review by colleagues of Cécile Gauthorn. Don't hesitate if you have questions, anytime again. Now, you know, I just said that it's not always easy to make a correspondence between the closure temperature of a certain mineral and depth, okay, which is important if you want to really do exhumation in terms of millimeters per year and not just the cooling rate. Well, people like Jean Brown have been very, very active on this, and this is an example from a different paper, but there's been a massive amount of effort, of scientific effort in modeling the different ways a rock can go from depth to surface, okay, and how this can lead to a cooling history of that rock that we then measure through thermochronometers. And basically, and Jean can explain that better, but basically the tendency now is to do a lot of forward numerical scenarios, and then look which one of those many scenarios give the temperature, cooling history that matches best the data. And there's always a range of scenario, but as you can see here somewhere in the middle, you know, of course, this is not a good scenario, but within certain uncertainty, we get very good constraints on the time, temperature, path of the rocks we investigate. Okay, another more very common aspect of tectonic geomorphology is to look at geomorphic markers. And now, not only look at them, but also date them. And so here is a famous type of setting, but there is a lot of geomorphic markers, you know, bay-headed streams. I think one of the most eloquent, if you are in a strike-slip setting like this one, which is inspired by the San Andreas fault system, is when you have a river which is laterally offset. So you have a motion on strike-slip motion on a fault, and that breaks your river and offset it. So if you date the generation of this offset and you measure the offset, then you get a fault slip rate on that fault. Okay, and a lot of people have done that. So for instance, there is a whole branch of let's say tectonicians who always go to everywhere in the world where there is a strike-slip fault. They do a trench and they look at the geomorphology. They do trenches, they date sediments, and they calculate slip rates. That's a whole branch of, and that can be absolutely fundamental for instance, for risk assessment. You know, to measure the fault slip rate and the recurrence interval of earthquakes, and that's all related to tectonic geomorphology. There are many other types of geomorphic indicators, and one of them, I will speak about it later, is something that, for instance, Alex knows really well, is nick points. So it's a little anomaly on the river profile that also preserves some tectonic signal potentially, or possibly climatic signal. But this is all, again, improved and enhanced by our ability to observe the Earth with satellite imagery, and also locally to measure the surface of the Earth. Okay, this is never exhaustive. I'm not trying to be fully exhaustive. I'm trying to cover a little bit, but I refer you to papers, and is to give you an overview. Now, one of the almost last point of this history is 1990 to present, and it's I think the development of approaches that look at sedimentary budgets, because that's really the link between upstream and downstream data in the sedimentary system. So this has also been done, you know, François showed this morning a paper, I think, by Gerhard Einzeller in Germany, who did that on the Ganj-Brahmaputra system. Einzeller is a precursor in this, and I think the paper was from the 90s. There is a whole book by Einzeller, which I also have here, which is also an amazing book, an amazingly modern book, but yeah, very precursor. And there was also other people, and now that's something that, for instance, the team of François and Cécile is doing a lot. But for instance, I took this paper because I found it also very, very important. That's a paper in which William Galloway, which is also a big name in sedimentology, for different aspects actually of his contribution to sedimentology. He worked a lot in the Gulf of Mexico, but he worked also in the North Sea basin. And obviously that's thanks to petroleum data that you can do that in those places, Gulf of Mexico or the North Sea basin. But with Liu, they made a synthesis of sediment volumes that they converted to rates of sediment supply. So I think it was already super modern to have this in thousands of cubic kilometers per million year. You see we are in 1,000 cubic kilometers, not in millions of cubic kilometers. We reach here much smaller volumes than what François showed this morning in the Einzeller exercise of the Himalaya system, which is normal. And here in this diagram, they put the rates of sediment supply to the North Sea basin, and they put it in front of the sea level curve, because one of the main, as you can see, this was one of the main environmental constraints we had to compare what we observe to some possible forcing factor. And so when there is a plus, it's that sediment supply increase matches with the eustatic sea level fall. So remember what I said initially about sequence stratigraphy. When you have a sea level fall, as you know, you develop a low stand system tract, and normally you have more land submitted to erosion, so your sea level is lower, so you should increase erosion globally, also regionally, locally. You should, for every sea level fall, you should see an increase in erosion and an increase in sediment supply to the basin. But as you can see, not everywhere. You know, here, for instance, you have a major increase in sediment supply at this time here, but it matches with a sea level rise. So this to me really embodies a lot of the reasons why we are doing what we do. First, is this correct? You know. Second, is this not completely biased by our resolution? Third, is this correct? Is the sea level rise here correct? Okay. How was it derived? And then, if everything is correct, what explains the sea level, the sediment supply increase at this time? So, if it's not sea level, if sea level is correct and it's not sea level, then is it climate or is it tectonics? But basically, these questions were here already, and so that's a paper from possibly 2000, but maybe the more the 90s. And here is when contrary to prediction, a eustatic low stand is not reflected in sediment supply changes. So that's where we have a low stand and no sediment supply changes. So it's a very interesting curve actually, very interesting data. This is another major paper by Pasaglia and Brandon, which are two major authors, I think, of tectonic geomorphology, and I mean they've done a lot of things. But in the times of basin, when basin research was still a young journal, 1996, they actually derived. They actually try to invert, if you want, or tell a story of the geomorphic evolution of the Appalachian Mountains in the US, thanks to the sediment supply to the passive margin. And so they used sediment volumes to derive the history of the mountain range. Okay, so you see they speak about a migrating divide here. Because when you start doing this, they were really the first to try to do a source to sink approach And when you start doing these things, you ask yourself questions such as this one: was my source area the same as it is today? How was my source area? How can I convert my volume into an erosion rate? Okay, and that raises many interesting questions that motivate further research. Okay, here I have another, I think, major paper, still in the same approach of sediment budgets, and it's a paper by Kuhlemann in a series of work by Kuhlemann, and we can see Fritz, who is also a PI in this group, as he was introduced this morning. In this paper, I think Kuhlemann also made a real amazing work in all these boxes. It's a bit of a Gerhard Einzel approach. Each of these boxes represents the volumes found in depot centers around the Alps, and so he made a synthesis of all the volumes around the Alps that he could constrain. From those volumes and their ages, sediment volumes from the Eastern Alps, sediment volumes from the Swiss Western and Southern Alps, he derived an evolution of the rate of sediment flux out of the Alps with time. Okay, and it is this range of curves. And as you can see, in the Oligocene, we have an increase, then there is some sort of plateau, a decrease here, another small increase, and then in the recent times, in the last 5 million years, a major increase in sediment supply rates out of the mountain range. And I think this is an amazing result to have such a history, a narrative of the evolution of fluxes around the Alps, because then you can look at all the papers and all the geological knowledge that is in this mountain range and try to figure out, why do I have an increase in sediment supply here? Why do I have an increase here? Okay, and that's how Kuhlemann and others discussed their curve. They actually compared their curve with everything that was known about the tectonic history of the Alps, and often when there was no match with the tectonic history, they concluded it was climate. Okay, so postulated main tectonic and climatic events controlling erosion rates in the Eastern Alps. And so I think it's a great exercise how good and how true this is almost secondary to the pragmatic evolution that this brings forward. I think pragmatically, this is really super interesting. So here, for instance, there is collision and slab breakoff, thrust loading. Here there is some collapse, updoming event, and here is a main extrusion period in the Eastern Alps. Here we have question marks, but here, sorry, the last increase in erosion rate is attributed to increasing glaciation, because we do not see major tectonic processes being able to explain such an increase in erosion and sediment supply out of the Alps. Okay, I think we could make a little break. I will not close my, I can just do perhaps stop sharing. We can make a little break and then come back in 10 minutes or 10-15 minutes. We do our 45 minutes period. I think it's large enough because you have it's going to be a long week. Maybe Cécile, we can stop the recording. Like this, we have little periods.
This is me, the
But,
in charge of. Hi, Luis. I don't see you.
you see, I can maybe do it, but I don't see it.
I did it.
Okay. Okay, so the last main period that I see as a major development, of course, in this history is the development of really the source to sink approach per se, with the name source to sink. Even if the name was already mentioned before, and sometimes we try to do the genetics of or the genealogy of where the name comes, but in the end of the 90s, there was a big project in the US. The US had a big program called Margins, and in the Margins they had different initiatives. One of them was the subduction factory. One of them was rupturing the continental lithosphere, and one of them was source to sink. And the source to sink approach really had a lot of the concepts that we still use today, and which were very, very influential. You know, just the white paper of this program was really influential in itself. Especially, I think there was a leap, so really a major step in the scale of the approach, and this was openly designed to bring the understanding of geomorphological, sedimentary, and stratigraphic processes to a substantially higher level. So that's Nitruer in 2001. And there was a different range of concepts. This was mostly directed onto margins. But really, in this first point, saying that the deposition here is shaped by processes that take place here, but also upstream of here. So really the source to sink concept is there. Then there is the systems approach. So I didn't say it before, but that's one of the major development, is to have a systems approach. And you know, you have, if you look in different universities worldwide, the research groups worldwide, not only in not in geology, but in many different disciplines, you often will see like you will often see the word system, and there is there is the discipline of systems biology, for instance, systems genetics. So it's when you start dividing and looking at your object of study in the sense of systems which have external inputs, which have outputs, and so this approach, this systems approach, is very important. It's one of the fundamental aspects, and the systems are connected. You see it on this profile or on this one. The systems are all connected, and the connections are boundaries which move. And why it's important that, for instance, the coastline, you know, the coastline is something which is moving, and that's moving in response to factors, eustatic, tectonics, sediment supply. So basically the motion of these boundaries between systems is what we can track in the past. We can look at these boundaries in our sedimentary record, and we can try to link it with changes of the deposition of the environmental factors. Okay, this is also a reference you can find. The margins website still exists, and you can find it on the web. Then, so this is major here, but I don't go more into this. I just can advise you to. I should give you the reference. I can give it to you like this in the chat. Chat. The reference of the website. So, sorry. And here is one of the last stage. And this was, I just put it afterwards because this was already in the margins program. And it's only emerging now, which now in the recent 5 to 10 last years. It's about signal propagation, which I think gives us a more dynamic view of stratigraphy. So here, this is a little diagram that was already in the margins white paper for S2S, so the proposal, if you want. And so the idea is that when you have a signal, you see here they put tectonics, climate, they put a drainage network which can change. For instance, drainage network can be modified, rearranged. This may give a sediment load signal, okay, maybe an increase in sediment supply through time in the mountains. How is this going to be transmitted down system all the way to the abyssal plain, you know, the Zumaya outcrop, or all the fans that Francois spoke about this morning? Same thing for a decrease, you know, and could it be transformed into something more complex than initially? And that's fundamental, because then we are stratigraphers. So what we see now is only this. How can we link this to this? How can we link this to this? Okay, so this is really signal propagation. How are signals transferred through those different little systems with boundaries between them? And this we worked a lot on this, and this is going to be, I think, Jean at least showed me. I don't know if he still will show you that, but Jean Brown has with the FastScape model that you can you will be able to use. Jean has incredibly nice examples of this, how signals are transferred from their source to their final repository. And we worked on this a lot with Brian Romans and colleagues. And in this paper, we conceptualized this also very inspired by the initial margins papers. And you will see in the rest of this week that a lot of the propagation, the ability of a system to transfer signals depends on what happens, for instance, in the transfer zone, whether this transfer zone is going to buffer or not the signals coming from upstream. That's Francois was mentioning the lakes as a buffer systems. And there is a response time also in this area that can change how we modify signals from source to sink. In addition, so here I have a, that's in the paper we did. We have a summary, but in the rest of this talk of this course, at the end of the week, I will take that in detail. Here we have a summary where we tried to summarize different types of signals in the source and how they can be transferred to the depositional area, depending whether it's a tectonic or a climatic signal, or if it's something linked with internal dynamics. What I symbolize here with those little logos is the functioning in the sedimentary system. So not an external factor, but an internal factor. Okay, and I will show you examples of that later in the course. Otherwise, we distinguish tectonic and climatic signals. It's a very simple difference, for the very reason that a climatic signal involves an increase or a decrease, for instance, in temperature or an increase or a decrease in precipitation. So that changes the ability of the geomorphic systems to transfer and transport sediments. Whereas tectonics, for instance, an increase in elevation driven by tectonics, will only increase erosion by increasing the slopes, but there will not be more water in the system unless you invoke feedbacks between the processes. Okay, so very last is about this autogenic effects, and I'm repeating a little bit something that was said this morning, but it's important. These are allogenic factors, and here I have autogenic factors. So autogenic factors means factors inside the system, and here there is this very this nice video from an analog laboratory experiment of a fluvial delta. This is in the St. Anthony Falls laboratory in Minnesota. And it's an annual paper review by Elizabeth Hajek and Kyle Straub. And what they worked mainly on here is on all the different little cycles and the whole dynamics that you can see here. You see, in this experiment, water discharge, the water input here, and sediment supply are constant, okay? Yet, obviously, the system is dynamic. So the question is how, I mean, this dynamic is obvious, okay? What we don't know when we look in the past is how much of this dynamic can take place at time scales over which we expect environmental factors to have been a signal. For instance, you know, these little lobes growing and disappearing and growing. If in nature this dynamic takes place at a time scale of 5 or 10 or 100 years, when we look in the stratigraphic record, we are not going to see that. If, however, it takes place over 20, 40, or 100,000 years or more, then this could look like a climatic or a tectonic signal. So there is a whole range of studies and a whole domain of science that tries to understand if this internal dynamics of sediment geomorphic systems can or cannot generate stratigraphic observations that overlap in time and magnitude with environmental signals. Okay, so I'm in advance. It's 3:30, and so François, I am actually finished. I don't know what you would like to do. I don't know if you are still here, François. Maybe, I mean, I can propose several things, but you guys, you ESRs, you are here to.
I'm here. Coucou.
Salut. I could propose different things. We could first I could show you the Molnar paper, because in this course normally I was asking the students to read the Molnar paper and then we discuss it together. I don't know with 15 students and more how this can work, and we don't have much time, so we could just look at it. I don't know if you've collected questions, but we could do a Q&A, question and answers period. It can be questions also about organization of the course in May, June. It can be anything. I could also see a possibility to use time is to ask all of you if you want to have help on the computer aspect that Jean is setting up. Maybe you've answered Jean already about whether you've managed to install to install the package.
I had a few discussions with some of the students about this, so it seems to work.
Okay.
I'm in a discussion with, sorry, I'm not used to all your names yet. Everton.
Yeah, that would be me.
Okay, Lucas asked a question. Do you think that autogenic controls get mixed up with climatic inputs in modern literature, much like climate and tectonics were mixed together in previous interpretations? I could do, you know, in close to where Francois lives, there is Normandy. And when a Normand answers to such questions, he says maybe. Peut-être que oui, peut-être que non. So, Lucas, I'm not sure. It's very possible that autogenic controls happen on those timescales that look very much like climate. I have more on this in my course, but you will see that so the group of Kyle Straub and also you know, all the students of Chris Fowler. I was just reading one of those papers here by Chris Fowler. They look at ways to try to identify and estimate, evaluate the time scale of autogenic variations, autogenic perturbations in a sedimentary system. And it's from their approach, it seems that there is much more autogenic possibilities than we think. I'm honestly not sure. Often I think we have concentrated on the time scale, and another aspect that we haven't looked at much is the magnitude. So perhaps autogenic factors do play a role, do take place at time scales similar to those of climate changes, like 20, you know, the orbital cycles. But I'm not sure their magnitude is sufficient to leave an imprint or to even overprint climate cycles.
I maybe want to make a comment, or we want to continue with this. Maybe there's a question by Philemon.
Okay, the Philemon is asking what are the autogenic estimated timescales within the sedimentary record. There is no such thing as an estimated timescale for autogenic signals, Philemon, in general. What I can just show you is here. I can show you an example of an autogenic signal. Here I will just share desktop. We'll come back to that, but since you asked the question, it's totally fine. But for instance, Wang, you know, in this paper, if you see my screen, they derived a time scale. So it's exactly the question you asked, TC. They developed a time scale for autogenic signals in channelized sedimentary deposits. In other words, the type of deltas that I've just shown before, or this one, which is the same actually, but here is view from above. You see it's again with Straub and Hayek. And this time scale they developed is actually L over a little r with a bar, which means average sediment rate. So NL is a characteristic length scale in the system, which is actually channel depth. So the channel depth in this system, if you see my mouse, there is a little channel. This little channel has a certain depth, maybe here 2 millimeters, because it's a laboratory flume, but maybe in the Mississippi it's 30 meters, okay? And there is an average rate of sedimentation in this area, which is basically, if the system is at steady state, at equilibrium, and we will work this out a lot with Jean, the steady state or the equilibrium sedimentation rate is often should be equivalent to subsidence. So if your system is at steady state and is subsiding, and there is sedimentation, then sedimentation equals subsidence, and that's the R. And so what they estimate for the lower Mississippi River with 30 meters here and 0.26 meter per kilo year for the sedimentation rate is a TC of 115 kilo years. So if this is true, then the time scale of autogenic variations in the lower Mississippi Delta has, Philemon, it has a time scale which is close to the climatic cycles. What is it? Eccentricity? I never know which one is which. But it's one of the orbital cycles, you know, very close. What we don't know is if this will overprint it or not, because maybe it doesn't have any magnitude. Maybe it's just the switching, you know, of the whole system happens on that time scale. But does it have an effect on stratigraphy that can overprint the effect of sea level changes? Because sea level change also take place on this time scale, but maybe with a much higher amplitude than the autogenic signals do. So I think it's interesting, your question and their answer, because at least it tells that from a first theoretical point of view, at least we cannot rule out autogenic signals. I wouldn't rule them out and say, oh, this does not exist, it's irrelevant. Actually, in Fastscape, Jean was also very nice examples. And it does seem to happen also in numerical experiments that you get some autogenic behavior. As soon as you couple erosion sedimentation in a little bit of maybe a non-linear way, perhaps it starts to take place.
I had a comment, maybe, Sébastien, very briefly.
Yeah.
It relates to both what you said and Francois showed about, you know, the big concepts in the source to sink approach. And I want to maybe refer to one of the examples that Francois mentioned, the North American one, you know, with the Rocky Mountains, and then it's very what he called I think the coastal plain, which is basically most of the rest of the US, and then the sink, which is the Gulf of Mexico. Mm-hmm. All I wanted to say is, of course, it's helps to think, to divide the world into a source, a sink, and a transfer zone. And to say that the source is where the erosion takes place, the sink is where the deposition takes place, and then the transfer area is basically is where transport takes place. But what's important too, especially if you start looking into the details or at smaller scale, all of these, the three parts of the system can undergo actually erosion, transport, yes, and deposition. And especially the transfer area, you know, what you mentioned, this autogenic cycles, which are related to, let's call them avulsions of rivers in a delta or even in a coastal plain, that these avulsions corresponds to localized episodes of deposition, transport, and erosion, depending, yes, on where the active channel is and its avulsions. But you could have, even at a much bigger scale, if the transfer zone that's at the foot of the mountain. Let's look now at the Pyrenees system. You know, the source is the Pyrenees, and the sink is the Gulf of Gascogne. It's the marine sink. But in between the two, you have what is now the, how would you call it, that fan? I keep forgetting the name of the fan, the depositional fan there. Merci, Francois. But and clearly, this is an area which is mostly dominated by transport, but also beneath that, there's actually the Aquitaine Basin. And so during some period of the life of that system, that transfer zone was actually an active subsidence, most likely when the Pyrenees were actively uplifting. And so in that, it was still mostly dominated by transfer, but also it was a sink. It was an important sink. So it's important to realize that they are mostly, the sink is mostly where the position takes place. The source is mostly where erosion takes place, and the transfer zone is mostly where transport takes place. But on various time scales and length scales, the three phenomena can happen all the time. You can have, terrace forming in the source area, and that's a depositional process. You can have a canyon forming in the marine system, and that's an erosional process in the marine system.
Absolutely.
So nothing of what was said is wrong, but I think it's important to realize that there are lots of scales both in time and space, and it helps to think in terms of source to sink, but let's not make just a big generalization that would contradict a lot of the observations. Absolutely.
And I would add that it's very important to have this in mind, that erosion, transfer, and sedimentation are like Russian dolls, these imbricated little dolls. At all scales, you can find that. And I think it's also important to have this in mind, because I think there is a link between time scale and spatial scales. When we go down to the very small spatial scales, if you go to the scale of a pebble, a pebble is moved during individual events, or a grain of sand is moved during individual events. So it's actually eroded, transferred, and deposited 100 meters later in the river. But this is, I think, the smallest time scales take place, the smallest spatial scales take place on the smallest time scales. So the basinal scale is really million years, often million years time scale. The terrace is kind of intermediate. It's maybe the climatic cycles. We can date that, but there is a link here. And so depending on the problem you want to solve, for instance, you're studying a succession and you have a million-year signal. Probably this is not linked with a landslide, okay? Because it's a million-year signal. It's probably linked with something that takes place at a longer time scale. So I think these are also imbricated. So I fully agree with what Jean said.
May I say that this is the goal of the project, and is really to know what's the accurate scale of observation that we have to do. And what is really important is to know what is the processes at the origin of change in erosion, sedimentation, transfer, to be able to be predictable. So it's why industrial people or societal implication will be possible. So if we are predictive about that, so it means that we have to be able to understand, to model that. And beyond that, the key question is, and for my opinion, this is something that is quite short in duration, is what's the critical time scale between autogenic and allogenic controls?
Who is going to answer that?
But for example, we have very nice database today, for example, talking about the Rhine system. There are so many dating on that system. We can know using that data set at what is the critical time scale for what is autogenic, pure avulsion with nothing, compared to something that is forced or by sediment supply or by a subtle sea level variation. So it means that, and maybe it might be interesting to ask people working on the Rhine-Meuse project to do conferences. So I think that that would be something very interesting to do and to have a discussion with them. So with the Utrecht group and all the people around.
No, absolutely. And it's a question that is very much at the moment looked at in all the projects. Amanda is asking, how would one quantify the flux to the sinks or to the sink or the strength of the climate tectonic event catchment with buffer zones such as lakes in the transport zone? How does one consider the time delay in sediment flux caused by these buffer areas within the system? You mean in a modeling approach or in a natural, in a real case? Amanda?
I think either. I'm just curious to hear what you have to have to say, because I'm just considering the two presentations we heard today. Earlier, we talked about different catchments with these buffer zones, like in the St. Lawrence, the Great Lakes, and how, if you're looking at the sink, you can incorporate this sink, incorporate this signal and how that moves to the system.
Okay, so I mean, there is there can be many different ways to look at this, but there is one very simple one. Is to take for instance, you take the volume of Lake Geneva and you divide the volume by the flux of sediment into Lake Geneva, and you will know how much time you need to fill it in. And basically, once it's filled, then the delta is here in Geneva, and there is not much lake. We can finally build a highway to circulate between Lausanne and Geneva properly. But that's the time scale of action of this buffer. And so I think, considering fluxes, we can look at this. I didn't do it actually for Lake Geneva, but this will be interesting to look at. You can also do it for rivers. You look at the height of a terrace and the slope, and you can and the size of the valley, and you can look at this. I guess we find things like 10,000, 20. We are again in those type of time scales. At the moment, for instance, the Lake Geneva is a huge buffer for everything coming from the Rhône Valley, because the delta in Martigny, so, south of Lausanne, is existing since the glacier retreated. So 10,000 years ago, the story started, and there's still no sediment that has come out of the valleys and Alps from outside of Lake Geneva. Everything is still stored into Lake Geneva. So it's a huge buffer. How do we fill that? So it's a deficit of sediment flux to the Rhône Delta. How does a deficit manifest itself as a signal? That's a question. When you have the presence of something, you can see a signal. Here we have a deficit, so I don't know, but that's a very good question. But always, I think a lot of those have answers in simple quantification or approaches of sediment fluxes. They are going to be the answer. I don't know, François, Jean, or Alex, or Fritz, if you have.
About Lake Geneva, Sébastien, what's at the bottom of the lake today, the sediments that is stored there? How much of it is actually only from the last glaciation? In other words, when you come back with the glaciers on top, do you flush everything out and you leave only, I know even for the Rhône Valley, this is not clear whether some of the sediments that deposited in what I call the over-deepening, the glacial over-deepenings, we're not even sure how old they are.
There is apparently each glacier, during each glaciation you carved, but you didn't carve out everything. So there is some, you're not on basement, or you're not directly onto the Mesozoic cover below Lake Geneva. There are other moraines, but from my understanding, they don't really know super well, that they don't really know it super well. And a lot of those moraines are lateral. there is places in Lake Geneva that are almost, you know, like a clean glacial surface. Especially on the northern coast, you see when you look at with the recent marine acquisition data, you see the stripes, you know, of the erosion of the glacier when it was there, and it seemed that it just retreated, and you have a fossil surface. But otherwise, at the bottom of the lake, you now have turbidites. It's Monsieur Forel, who gave his name to another institute in our section. And Monsieur Forel was one of the first one who discovered turbidites. So he actually demonstrated that the sediments that come from the Rhône and reach the coast in Martigny, Villeneuve, not everything is stored at the beach. A lot of it continues down the delta and goes being deposited at the bottom of the lake in the form of sand. In the past, people thought that in the middle of a lake you have mud and you have sand on the coast. You have a grain size organization with coarsest on the coast and muddiest, finest in the middle, because it's where there is the least agitation. But Forel actually demonstrated that you have turbidites going down all the slope, like you were saying before. You have little canyons that bring sand in the middle of the lake. But I don't know if anybody has calculated the rate of advancement of the coastline into Lake Geneva.
I think I also, you know, Frederick Herman showed me the work of someone else who works in Lausanne, and even there is a very strong seasonal cycle on the fan activity, depending
Yes.
on, you know, how much sediment, and I think it may even be the temperature of the water, but
Yeah.
sometimes the you know,
Yeah,
the flow.
you change the stratification of the lake between winter. In winter, you have no stratification, and it's the migration of the thermocline in the lake, and yeah, you get a quite strong change, and this is important for sediment production because you have a lot of organic matter preserved in the deep lake. Yeah.
And Fritz was in a project, a Synergia project, in which they studied, because there is a lot of hydroelectricity plants in the valley, which has an effect on flux, sediment flux, and water discharge. And there are a lot of other plants and other human disturbances in the catchment, and all of this was kind of quantified. So I could actually find the answer to the question you asked exactly, Amanda. But in the case of Lake Geneva, for other lakes, I really don't know. I mean, the glacial lakes I know of, probably we know of them because they are not filled. Maybe there are many that are filled, but now that I think about it, there is a paper by a guy called, I think, Blother in the Himalaya, where they quantified with Schwangart and maybe with Dirk Scherler, maybe that's a Potsdam Potsdam team, Jean, where I think they quantified the effect of terraces and ice, dammed valleys. It's with Oliver Korup. Oliver Korup. Now it's coming back to me. I should find. I could find the paper, but they found quite an important buffer effect of those areas.
Yeah, the key question is the question that asked Jean. So it's to know if you can preserve some sediments from one glacial stage to another one. So or if you remove everything at each cycle by glacial erosion. So, yeah. And the point that I want to insist on, and this is based on the Great Lake in North America, is that the kinetic of the sediment supply is not linear at all. You get a paroxysm at time of melting and just after the melting. Okay, so it means that this is between 14 and 8,000 year BP that you get the maximum rate of siliciclastic supply, and after you decrease it to get something that is almost non-active, and this is the case today.
So it means you have two effects. You decrease sediment supply and you have a huge buffer in front of any.
Yeah, yeah.
So you have really clear water out of Geneva. Okay, so it's really these kind of effects are really interesting. Just to also rebound on this, you know, there's a lot of interest into those glaciations, the carving and their effect, their recurrence, how they behave with time. Here in Switzerland, for instance, they want to bury nuclear waste. Okay, and Switzerland is a small country in the foreland, in front of an orogen. Of course, there is no huge hope that the glaciation comes any soon. But if they ask the question, the people from the NAGRA, the agency for monitoring the radioactive waste, they ask to geologists, where is it that we should bury nuclear waste, to what depth, to avoid that the next glacier that digged out, you know, something as deep as Lake Geneva, 400 meters deep, where should we bury our sediments such that we avoid it being exhumed during next glaciation. So we know the time scale of radioactive waste is potentially 100,000 years or more. So they do worry. It doesn't seem like an immediate concern, you know, in terms of COVID, but they do worry that barrels of nuclear waste will get exhumed by the next glaciation 100,000 years ago. I don't know if it's just the Swiss or if everybody does that, but they are really. I was amazed when I heard when I heard that, because I think it's a great worry to have. If you can worry for the human beings who will be here in 100,000 years, that they don't get too much of our waste coming back, like now, you know, there is this Otzi Austrian mummy coming out of a glacier, but maybe in 100,000 years it will be barrels of nuclear waste coming out of glaciers. And so I think it's a great worry to have. If we can avoid that, it's the least we can do.
Sébastien, if I can just complement what the question for Amanda.
Yeah.
I read a study that is about the fluvial system I'm studying now in the moment, the Meuse River system. And they estimated the amount of sediment that is being entrapped within a buffer zone. This buffer zone is the Ruhr Valley Graben here. Mm-hmm. So what was done basically was they mapped the pre-Oligocene planar surfaces, and with that they put all the data in a GIS environment, so they can estimate the amount of sediment that has been eroded if compared with the modern topography. And with that, then they compare with the amount of sediment entrapped within the Ruhr Valley Graben, and then they can estimate how many % of sediments in total can be entrapped within this buffer zone. So it's just an estimation, of course, but I can send you, Amanda, later the link for the paper, and you can have a look on that.
So this is more of a volume estimation.
Exactly.
So they consider that some of the sediment, so it's like Jean was saying before, is that this place is a sink as well. It transfers some sediment, but it's also a sink.
Exactly.
And therefore, some of the sediment does not make it to the sink. Mm-hmm. It's trapped on the way.
Yeah.
But in this case, do they speak also about a time delay or an effect on the arrival time of the signal?
If I'm not mistaken, they do, but I'm not so sure.
Okay.
I have to check in the paper.
Okay. Caroline is asking if any of the ESRs will look into the impact of human-made buffers. And I think Ariel may actually do, but I'm not sure in what, to which extent. Ariel Doprado, who is in Bern. And also there is another ESR working in India with Sanjeev Gupta, who will be based in London. And both Ariel and this other person not yet recruited do have an interaction with human timescales. Ariel, you can comment if you want.
Yeah. Of course, it's a little time scale because we know the size of this time scale, but I'm working on that and comparing. For example, the grain sizes is a way to see or to measure the sediment supply, and the main idea is compare with rivers that are in natural state and see if for the same climate and same slopes we have different cases, not only on the case of the check dams, but in canalization too, because those things can change the characteristics of the river and capacity of transport, even in volume and grain size too.
Yeah. So in the place where Ariel is working, there is some rivers which are still very natural, and some are a bit less natural. So the people who have made the human modifications, they also kept a record of what they did and when they did it. So it's a useful. These are useful archives to cross geomorphic and human timescales. And I think the idea of Sanjeev Gupta in India is to do the same on a large alluvial fan with archaeological remains. That's something quite interesting here, because you can make a link. I think at the moment that's something that is being developed is the link with archaeology, because you can study how ancient perturbations have had an impact on ancient civilizations as an analog to what modern perturbation may have as an impact on our civilization. So there's a link with archaeology there that can be interesting. Bitte schön. Okay, I think it's 4 o'clock, and François or Cécile will teach again. Perhaps we can do a break, but I think the Zoom remains open.
Good idea.
Yeah, François, when you start again, I will remind you to record for.
Yeah, I stop at the moment. Okay, and hi everyone. Are you around? May I start? Who's there? Everton is there. Okay, there are a couple of people, so yes, I have to start again. Okay, so I have to share my screen.